Hello, students. In this video, I'm going to discuss an important question related to nuclear physics. It is based on Mossbauer effect. See, the question says, suppose there is a nucleus which emits a gamma photon and it doesn't recoil. The nucleus doesn't recoil, then energy of the gamma photon is E. Now, consider another case where the nucleus emits another gamma photon, but it recoils freely. So in that case, energy of the photon, emitted gamma photon will be different. So question is, uh, if nucleus recoils freely, then calculate fractional change in energy of photon, gamma photon. Okay, basically. So these are the options given. Okay, so you can attempt this question. Okay, you will be able to get one of these options. And if you cannot solve, then you look at the solution that I'm going to provide here. Okay, so let's solve it. See, the question is, there is a nucleus. Its mass is m, and it is emitting a photon. Okay, so initially it is at rest. Okay, now it emits a photon and it is not recoiling. It has been, suppose, fixed in some crystal. Okay, as it is done in Mossbauer spectroscopy. So it is embedded in some crystal and it is not able to recoil. Okay, so here there is no recoil. Okay, so in that case, it is emitting a gamma photon and it has energy E. Now, obviously, if it emits gamma photon of energy E, then its mass will become m minus E upon c square, because it is emitting this much energy. Okay, so mass will decrease by E divided by c square amount. Okay. Now, consider another case, third case here, where it emits a gamma photon and it recoils freely. So this is free recoil. So if it recoils freely, then what will happen? It gains some speed in this direction. Okay, so let's say now in this case, energy emitted is E primed. This is the energy of photon. Okay, so question here is we have to find this E minus E primed or divided by E minus E prime divided by E. This value we have to find. This is the fractional change in energy of the photon. Okay. So obviously it has emitted a photon. It means actually देखिए यहाँ पे आप सभी जानते हैं कि गामा फोटोन इमिट होता है बिकॉज ऑफ सम ट्रांजिशन इन एनर्जी लेवल ऑफ द न्यूक्लियस. ठीक है, तो ट्रांजिशन तो सेम हो रहा होगा यहाँ पे. सो एनर्जी ऑफ द फोटोन विल डिक्रीज बाय द सेम अमाउंट. ओके, तो यहाँ पे भी इसका मास जो होगा ना वो m माइनस ई अपॉन सी स्क्वायर ही होगा. ठीक है ना, जैसे इस केस में हो रहा था, बिकॉज इट इज इमिटिंग द एनर्जी, सेम अमाउंट ऑफ एनर्जी, बट नाउ दैट एनर्जी इज बीइंग शेयर्ड बाय द इमिटेड फोटोन एंड द न्यूक्लियस इटसेल्फ. तो वो एनर्जी दोनों में शेयर हो रहा है. ठीक है, ऑलराइट. सो नाउ लेट्स से, सो दिस इज द सिचुएशन नाउ वी हैव. तो इसका देखिए ये फोटोन है, दिस इज गामा फोटोन. तो इसका मोमेंटम अगर आप लिखेंगे तो इसका मोमेंटम तो हो जाएगा P इज इक्वल टू ई प्राइम बाई सी. So according to conservation of momentum, it was initially at rest. So initial momentum is zero. So final momentum should also be zero. तो इसका भी momentum, जो न्यूक्लियस का momentum इधर होगा ना, P is equal to, वो भी इतना ही होगा, E dash by C. Mass is this much. So if we say that momentum of photon is E prime by C and momentum of nucleus is also E prime by C, it means we are applying conservation of momentum. Okay, क्योंकि इन दोनों का टोटल मोमेंटम जीरो हो जाएगा, विच इज इक्वल टू इनिशियल मोमेंटम. सो that ensures the conservation of momentum. All right. Now let us apply conservation of energy here. So we are going to apply here conservation of energy. So we'll say sum of energy initial should be equal to sum of energy final. So energy initially photon was nucleus was at rest, so it has rest mass energy mc square. बाद में आप देखिए इस फोटोन की जो एनर्जी है वो ई प्राइम्ड हो गई. ठीक है ना, और इसका जो न्यूक्लियस का एनर्जी होगा वो हम लोग ऐसे लिखेंगे, इसका ऐसे लिखा था ना, पी स्क्वायर सी स्क्वायर और प्लस. अब इसका जो रेस्ट मास है, मान लो ये जो मास हम लोग लिख रहे हैं ना, दिस वी आर सपोज राइटिंग एम प्राइम्ड. ओके, तो यहाँ पे ऐसा हो जाएगा एम प्राइम्ड स्क्वायर और सी पावर 4. सो लेट्स put the values. mc square is equal to, this is e, या इसको ऐसे लिख देते हैं, let us write it like this. take it to the left side. Okay, so this becomes mc square minus e primed is equal to, let's put the value of p here. So it will become e primed square by c square. So therefore we get here e primed square और plus, ठीक है, m प्राइम्ड स्क्वायर हियर, ठीक है ना। तो m प्राइम का वैल्यू हम लोग इसमें यहाँ से पुट कर देंगे, दिस इज इक्वल टू m माइनस e डिवाइडेड बाय c स्क्वायर whole square, and here we get c power 4. So let's square both sides. So if you square it, what you will get is इसका स्क्वायर हो जाएगा mc स्क्वायर माइनस e प्राइम्ड, इसका होल स्क्वायर हो गया, दैट इज इक्वल टू, यहाँ से आ जाएगा e प्राइम्ड स्क्वायर प्लस m माइनस e डिवाइड बाय c स्क्वायर एंड होल स्क्वायर, and here we get c power 4. All right. So let's open the bracket. So we get m square and c power 4 plus e square or minus 2m and c square एंड ई प्राइम दैट इज इक्वल टू ई प्राइम स्क्वायर और प्लस, इस ब्रैकेट को भी ओपन कर रहे हैं हम लोग, ठीक है ना, और सी पावर 4 से मल्टीप्लाई कर देंगे. सो इफ यू ओपन द ब्रैकेट यू विल गेट एम स्क्वायर सी पावर 4 माइनस 2 m e and c square, and here you will get c power 4 कैंसिल होगा, so you will get here e square. Okay. Now you see कुछ factors इसमें cancel होंगे. This m square c power 4, m square c power 4 cancel out. Okay. This e primed, यहाँ पे sorry e prime था ये. This is e primed square and this e primed square, this cancel out. Okay. So now you bring this term on to the left side. Okay. So you will get 2mc square term common, and you will get here e minus e primed. Okay. There is e primed here. All right. And on the right side you are getting e square. Okay, this is e square. So therefore if we divide both sides by e, okay, then we'll get here e minus e primed or divided by e, and this 2mc square I'll take in the denominator. So you will get here 1e because we have divided by e, so e square becomes e now here. So this is 2m and c square. So that is the fractional change in energy of photon, ठीक है, due to recoiling. Okay, so if photon nucleus doesn't recoil, then it is emitting a photon of energy E. If nucleus recoils, which generally happens, okay, so it emits a photon of energy E primed. So here, because of the recoiling, okay, because of this recoiling, okay, fractional change in energy of the photon will be equal to this much, E divided by 2mc square. So this was a small application of energy momentum conservation from relativity to the concept of nuclear physics. All right.